Alright, now we're going to look at some of the calculations that we're going to be doing with kind of the basic properties of frequency, period, and velocity of a wave. The equations we're going to use are these 5. So frequency, we mentioned in the previous video that that's how many waves go by per second. So if you know the number of waves and the time, you just divide. Period is the inverse of the frequency, so that's how much time per wave. And so if you know either of those, you can find the other. We've also got this equation here, which tells us the speed or velocity of the wave, which we get by multiplying frequency times wavelength. Okay, this equation here applies to all waves, whether they're longitudinal or transverse, or whether they're electromagnetic waves, which we haven't really talked about yet, but any type of wave will follow this relationship here. And if we look at the units real quick, units for frequency are waves over time. Now waves is just a number, you're just counting waves. Time is going to be measured in seconds. So the units of frequency are inverse seconds, and we redefine that as what we call a hertz. So 1 hertz is 1 inverse second, or 1 wave per second. So that's our units for frequency, inverse seconds. Wavelength is a length, so that's meters. So if we have inverse seconds times meters, then that just gives us meters per second, which is what we want because we want a velocity. Okay, this bad boy over here, we can find the speed of a wave on a string. So this only applies to waves on a string. This doesn't apply to sound waves or something like that. Waves on string. Okay, so this guy here. Now the speed at which a wave will travel on a string depends on the physical characteristics of that string. So kind of qualitatively, you can see how this makes sense. If a string is pulled tighter and you snap it, it's going to snap back quicker, so that allows a wave to travel faster. So increasing tension increases the wave speed. If the string is thicker, like a big heavy rope, that essentially gives it more inertia. This quantity in the denominator here is a linear density. Normal density is mass per unit volume, but you can think of a linear density, mass per unit length, if you have something like a string or a rope. So if it's got more inertia, it's going to snap back more slowly. So thicker ropes or thicker strings are going to have waves travel more slowly. If you want to see the full derivation, you can hop on Wikipedia and just find the vibrating string article. It takes a little bit of calculus, but if you want to see it, it's there. Alright, in case you forgot what these symbols are, period, wavelength, frequency. By the way, for period we use capital T because this isn't any time. You can't have time on both sides of the equations. This is the specific time for one wave cycle or between waves. Okay, so be careful to use capital T's when you're looking at the period of a wave. Okay, let's work through a couple of examples. Let's say we want to know the wavelength of a sound wave of middle C on a piano. Okay, the frequency of middle C is 261.6 hertz. Okay, and we want to find the, sorry, I lied. Go back. We want to find the wavelength of that sound wave when we're listening to middle C on a piano. So in order to find that, we're going to use, we don't have a relationship just between frequency and wavelength like we do between frequency and period, but we do have frequency and wavelength in this equation here, V equals F lambda. Now we need to know the speed of that wave. The speed on the string is different, but once that vibration leaves the string and goes into the air as a sound wave, it travels at the speed of sound. Now the speed of sound varies slightly depending on pressure and temperature, but for our purposes we're going to use 343 meters per second. That's at standard temperature and pressure. Okay, so if we plug in the speed of sound here, then we plug in a frequency of 261.6, Then all we got to do is solve for wavelength, and it turns out to be 1.31 meters is the distance from one compression to another in that sound. Alright, now let's say we want to know the wavelength of a radio wave. So if you tune your radio to a radio station, let's say 100.1 FM or something like that. That 100.1 is actually the frequency, and on the FM dial, those frequencies are all megahertz. Mega means million. So this is 100.1 times 10 to the 6th hertz. And if we want to know the wavelength of that, we're going to use our same equation, V equals F lambda. Now, if it's a radio wave, that's what we call an electromagnetic wave. Again, we haven't talked about that too much, but electromagnetic waves include light and infrared, ultraviolet, X-rays, those kinds of things. And they all travel at the same speed, which hopefully you remember, the speed of light, 3 times 10 to the 8th. So we plug that in for velocity. We've got our frequency, 100.1 times 10 to the 6th, and then times wavelength. So we just divide that over, and we can solve for wavelength. In this case, it comes out to be 2.997 meters. So actually fairly close to the wavelength of that sound wave. I mean, given that this could have been, you know, miles and miles long or nanometers or something, those are fairly close to the same wavelength. Alright, let's look at a couple other examples. Let's say we want to know the speed of a water wave. Say you're sitting on the beach enjoying your vacation, and you count in 1 minute. You say that there are, you don't say, you count that 12 waves lap up against the shore. We would also need to know the spacing between the waves, or the wavelengths, and let's say that when one wave is hitting the shore, you look out there and you estimate that the next wave is about 20 meters away. Okay, so you can use this information, and I want again to find the speed of those waves. So again, we're going to use V equals F lambda. So we've got lambda, that was given. V is what we're going to try to find. So what about frequency? Well, I've got 12 waves in 1 minute, so I can use my equation for frequency, which is waves per time. So that's going to be 12 waves, and I want this velocity to be in meters per second. So this time I'm going to convert to seconds. So 12 over 60, which is 0.2 hertz, or 0.2 inverse seconds. So I can plug that in here, 0.2 times 20, and I get a wave speed of the water waves coming in at about 4 meters per second. Not too bad, huh? Alright, let's look at one more example of a wave on a string using that other funky equation. So that equation was V equals square root of the tension in the string divided by the mass per unit length. This whole thing is under the radical. Okay, and let's say that we are a telephone line worker, and we're putting up a new telephone line, and we want to make sure that we have about the right tension. Let's say that the tension for our cable has to be less than 1500 newtons, otherwise the cable will break down and break eventually. Okay, so let's say we know some information. Let's say that the telephone poles are 40 meters apart. We know that the mass per unit length of the cable that we're using is about 0.5 kilogram per meter. And in order to find the tension, we can find, if we know the wave speed, we can solve for tension here. So let's say you pluck your cord here, this wave travels here, when it reaches the other pole it actually reflects and bounces back, and let's say the time for that wave to go there and back was 1.5 seconds. So if we know this, this, and this, we can get at this. So to find the velocity, we know the distance this traveled. It went there and back, so my velocity was distance over time, so 80 over 1.5 is my velocity. And then I can plug that into this equation here. So I can say 80 over 1.5 equals square root of tension over my linear density here, my mass per unit length, which was 0.5. And now I just have a bit of algebra. I can square both sides, so I'm going to get tension is equal to 80 over 1.5. It's kind of an ugly 8. That got squared, and then bring the 0.5 up. I'm kind of skipping a bit of the steps in algebra here. Anyway, so that's what you're going to have to plug into your calculator, and turns out that you have a tension of 1400 newtons, if that's the time it took for your wave to travel there and back, and we needed to be below 1500, so we're good. And if our time had come back something less than 1.5, then our velocity would have been greater, which would have meant greater tension, and so we would have needed to decrease the tension in that case. But anyway, there's another example, and good luck on your homework.